So office hours were a little lonely on Friday, but yesterday we had, I think, a good conversation. So that recording from office hours does not exist from Friday. Thanks, Mike, for showing up. But because he was the only one, so we just kind of like aborted mission. But last night we had a good 4 people show up for office hours, so that is on YouTube. I got it up last night. Yay! So anyone have any questions they want to ask first on the open homework assignment number 6, the one that's finishing up the longitudinal MLM analysis? I honestly did not get a chance to look at the discussion board right before class because I was getting your next assignment polished. So maybe we should go there.
Oh, sorry.
Yeah.
R squared and ICC, because so that's like prompt 2, and I think a part above that. I was just a little confused about like how they're different and
how they're different. Yeah, R squared and ICC are very overlapping. ICC is usually only calculated on just the true null model with nothing in it. But sometimes we do it on a conditional model with other terms in it. It has some more complexity. So R squared is usually what we use when we start adding terms into a model. Now, both ICC and R squared have at least 2 versions of them, and R squared has about 37 different formulations, right? So it's got 3 or 4 that are most common. So I want to pull it up. Yeah, so pseudo R squared, marginal R squared, conditional R squared, conditional and adjusted ICC. So we're going to look at that. Yeah, spacing. Yeah, the base. Okay, so this is one thing we talked about in the office hours. So those of you that haven't had a chance to watch that or attend that, you might have this a question. So you're not doing it wrong if your likelihood ratio test using the ANOVA command says this model's better, but then when you do the compare performance, the Bayes factor performance score prefers a different model. That's a contrast. They're not in agreement, but that doesn't mean you did anything wrong. The likelihood ratio test has been the gold standard for years and years and years and years. The Bayes factor with the performance score is a newer method, and just kind of on the surface, my experience with it is it tends to prefer simpler models. Now, there's a lot of times whether we're using AIC, BIC, ICCs, R squareds, there's a lot of different ways you can compare models. And all of those comparisons are not always going to agree what's the best model. And so the best thing to do is use your theory as a guide. We're always trying to balance the complexity of real life with noise. So we're trying to find this balance between the model that explains the most in the data and the one that's parsimoniously theory driven. And so in the case of the homework, I think it's the 3-way interaction, the ANOVA method, the likelihood ratio test, the deviance difference test, whatever you're going to call that thing, that prefers the model with the 3-way interaction. But when you do the Bayes factor model, it wants the one with the only one 2-way interaction and sex not interacting with anything. I think it's model 2 versus model 5, depending on how you number them. So in real life, you would choose the one that has more theoretical foundation. Is it reasonable to expect those 3 things to all be interacting, that both of those 2 things are moderating trajectory over time? And if there's some like foundational reasoning, yeah, that's reasonable, and that's something we want to look at, then definitely include it. The likelihood ratio test, I would go for that. I would take that suggestion over the Bayes factor. Most of the time they're going to agree, but you will run into times when whatever method you're doing, that there's multiple fit statistics and they might not all agree. Okay, we still need to do ICCR squared. I'm just trying to see if there's anything else here. Okay, I think this is, yeah, so there are times when the simpler model will be best. And a lot of times that's if you have no biological, physiological reason why you have variables that should interact. And you think it might be picking up more of noise. all data has noise in it. And we hope that we're getting the signal and not the noise coming out in our models. And we cannot guarantee that our model is picking up only signals. Sometimes we can have flukes in our data. And that's why, how many studies does it take for us to document what the truth is? One study? One study the truth does not make, because we might have fluky data. And I think we're seeing that right now the world is seeing science in action. And what do we see on COVID? One study comes out and it says this. And then a week or two or a month later, another study comes out and it says something slightly different. And everyone's like, oh no, which one's wrong? And who did what wrong and trying to blame. And it's not really blame. It's every time you take a sample, even in the best case, you're going to have noise in that sample. And that's why you might get something unexpected, or you might get an interaction showing up as significant that really has no business having an interaction. So there are those are the times when you might go with a simpler model. In this case, I would probably go with keep the three-way interaction in the final model, since it seems reasonable that sex could moderate group differences over time, and because the likelihood ratio test picked it to be better, to fit the data better, even though it was more complicated. Okay, so residual plots. The residuals on this one were not terrific, so let's look at it. Residual plots. So residual plots for diagnostics can be problematic, because no data set is going to have perfect residuals when you get into the wild caught data. It's always going to have some, it's not perfect. And so being able to train your eye to kind of know whether the residuals are good enough or they're concerning enough is kind of an art, and it has a lot of exposure is the best thing for developing that feel. Didn't think this is how statistics was, right? You go by feel. But most people do not publish their residual diagnostics, right? Who's seen residual diagnostics in a final publication in print? It doesn't happen. If someone publishes a model, it is assumed, it's a dangerous thing, that they did residual diagnostics and they were all clear. Because if there was a problem in the residual diagnostics, they should have said that and tried something else. And so using R, the way we're on our homework, how easy is it to run residual diagnostics and include those in a supplemental material? It's cake, right? It doesn't take that much typing for you to create the residual diagnostics. Now, the main reason they're left out of a manuscript is because A, people are lazy, and I think they're not doing it as much as they should. And two, it's space. We are always trying to cut stuff out of our manuscript to get it to fit in the allotted space. But using supplemental materials, especially knitted R documents, allows you to include those in with your article. And I think that that would help everyone develop an eye for residual diagnostics and help everyone be transparent and reproducible and hold each other accountable for actually doing residual diagnostics instead of just trusting that people did it. Okay, so let's go into R. Oh, that's the book. I don't want to open the book right now. Let me open a new R. Usually if I'm doing multiple projects on my computer at a time, which is like every day for me, I will open up a new R Studio for each project so that I don't get stuff overlapping in the global environment, especially because I tend to name things like data wide and data long and different projects, and I don't want to get them confused. Okay, so I'm going to open the key to homework 6, and just because it's already typed in. So let's go down to here. Now I better make that bigger because I don't think you can see that because I can hardly see it. Let's see. Okay, thumbs up if it's big enough, thumbs down if it's too small still. Jill, is it still too small?
I actually have you pinned right now, so I'm trying to switch it.
Okay. Let me know
if it's
too small. What?
I got it. It's great.
Okay. All right, so this was, let's see, our first model we calculated. This is a truly null model. Truly null because it only has fixed intercept and random intercepts. It has no predictors whatsoever in it yet. This is truly null model. When we do the ICC, both numbers will be the same. And when we do the R squared, the conditional number will be that same number. So this is the simplest situation. So that R squared of 0.24, that is the variance in all illness severities at all time points, how much person-to-person differences there is across all time points. So if we just had a pot of all those illness severities, knowing which ones go to who accounts for 24 or about a quarter of the variance. So that's probably the easiest one to talk about. Now this marginal R squared is 0. And the reason is the marginal is only for the fixed effects. And what fixed effects are in this model? Just the intercept, and that's just the average. So that doesn't really explain anything. So on a truly null model, the marginal R squared will always be exactly 0. The conditional R squared will be both equal to both the adjusted and conditional ICC. So that's the simplest way. Now there's nothing about time in this model, right? No time in this model whatsoever, let alone any other covariates. And then we step up to the next models. So let's go to this one right here. This one we're calling 0RE, at least that's what yeah, 0RI, RI for random intercepts. So we still have one random intercept per person, but now we're putting in OBS, that's our time indicator, equally spaced treated, 0, 1, 2, 3, 4, and on. So now when we do our ICCs, now let me get it. ICC and R squared will not all be the same. We'll get 4 different numbers. They're all slightly different. They're all kind of in the same ballpark. We're 26 to 58, but it's not the same number. I'm going to come over and I'm going to put a question mark and I'm going to say for performance ICC. I'm going to do this first, and it's going to bring up the help page for ICC. And after the help page lays out, you know, the description, the usage, it has this detailed section. So ICC tells you the proportion of variance explained in the outcome explained by the grouping structure. ICC only tells you about the grouping structure. That's random effects. So then if we come down a little bit more, it talks about adjusted versus conditional. So that's why we have these 2 here. So both take into consideration all sources of uncertainty or all random effects. The adjusted only relates to the random effects. The conditional also takes into account the fixed effects. So this is a really good source for that. Oh, I think it's the other one it talks about, R squared talks about Hawks. But typically the adjusted is of interest when the analysis of random effect is in interest. So sometimes we want to know about the random effects. Random effects are the thing we're studying, the purpose. We want to know about percent variation due to grouping. We want to know how similar students in the same school are. It's rare that that's what we're into, but sometimes that does come up. Usually more often, the clustering is a fact that we don't really care about quantifying. We just want to control for it. So in repeated observations, it's kind of a given that if I measure the same person, their repeated measurements are going to be correlated because they're the same person. We don't necessarily care about the number that is, but we don't want to ignore that. So we want to control for person-to-person differences. That's why we don't have just one person in our sample or 2. We want a good number of subjects so that we can control for subject-to-subject variability. So the adjusted would be what you would be concerned about if you wanted to know how similar or different are individuals as a whole. Here with random intercepts. And now this model has OBS in it. OBS is a predictor. So this number really only refers to the baseline measurements. So there's 43% of the variance in baseline observations, baseline illness severity is attributable to person differences. Now that's the adjusted. Is just.
Can I ask what you mean by baseline?
So baseline is the first observation because now we have this OBS in there. So these random intercepts are only talking about, the random intercepts refer to when OBS is 0. And OBS is 0 at baseline.
Got it.
Yeah, I had the same question. I was wondering how we would know that.
Yeah, it's because these random intercepts, the intercepts are defined when all the predictors are 0. So the 43%, so when we did it up here, without OBS in it, this is 24% of the variance in all illness severities is explained by person-to-person differences. This one now tells us how much person-to-person difference in illness severity there is at baseline because we have that slope over time included as a fixed effect. So the conditional is just person-to-person differences at baseline. Yeah.
Okay. Is that why, does that mean that it's pretty important to have your first time point labeled as 0?
Yes, or some other meaningful time. So most often if we're doing trajectories, we want 0 to be our baseline, but sometimes we don't want it to be baseline. I've worked on studies where we had multiple baselines and then multiple intervention. If you're doing N of 1 or single subject design, this happens a lot. You have multiple baselines and you want time 0 to be when you switched from that baseline phase into the intervention phase. So the intercept would refer to that changeover point. If you center.
So that special number you would adjust so that it's 0.
Yes, so this is why it's important for whatever variable you're using for time that it has a meaningful 0 point. So that's why we centered it either at baseline or center it at some crucial midpoint. There's a really famous study, a multi-level model longitudinal studies that looks at elementary, junior high age girls, their body fat percentage as they age from like age 7 to age 18. And what happens to girls' body fat percentage? Does it go straight? Does it stay flat? Does it go up? Is it a straight line? Girls, what's body fat doing? What crucial thing happens somewhere between about 6 or 7 and about 17, 18?
Puberty.
Puberty, we love it, right? So it actually ends up that the body fat goes kind of slightly up and then it hits puberty and it like goes way up and then it plateaus. So in that point, you'd want 0, the time point, to be puberty. And that's how they did it. They measured these girls in their school every year. And then they asked them every year if they had started their period. And then that date, that month, becomes the 0 point for each. So each person has a different 0 point, but that 0 point means menses started. So it has a anchor point. So the worst thing you can do is leave time 1, 2, 3, 4, 5.
Really cool.
It is a really cool example. It's the first one study that I read about. And I got it over here in this book. It's really, I like stuff that are like real world issues. It makes it a lot more concrete than widgets in a factory, like in junior high math. Anyway, so this 32% is the proportion of variance in baseline illness severity that's attributable to person differences. This adjusted R-squared includes the adjustment of time effect. So now with the adjusted R-squared, we'd say 43-ish% of the variance in illness severity is due to person differences at baseline and linear growth over time. I'm saying linear growth over time because OBS is not squared. It's just the variable name plane, and that means linear growth. If we had OBS and OBS squared, it would be parabolic or quadratic growth. Okay. Does that help clear up? So that's the ICC. Help clear up the ICC? The conditional is just at baseline. The adjusted is baseline plus linear growth in this case. I'm going to come up here and I'm going to now look up the help page for performances R squared command. And just, okay, so we have to look at the right one. So for a mixed model is using this one, Nakagawa, which is, it's selected as the baseline for mixed models because it's kind of the currently agreed upon best one to use for mixed models, which changes over time. But you'll notice, interesting, I think it's in here. Look at who is referenced. His first reference is volume 2 of our textbook. I told you it's a good one. And then we've got Nakagawa, I'm probably slaughtering it. He is on all these other publications. So the marginal and conditional R squared values for mixed models are calculated this way. And there's the citations, you can read more about it, like anyone has that time. But marginal R squared is only the variance of the fixed effects. So this is, so the 0.32 is just differences, person-to-person differences at baseline. This marginal R squared is how much linear growth explained. And then if you combine them, it's 0.43. Now they don't add up because there's some overlap. So person-to-person differences at baseline account for 32% of the variance, and linear growth accounts for 26%. If you combine linear growth and person-to-person difference at baseline, it's 43%. They don't exactly add up because the distribution of variance is at level 1 and level 2. So there's time and person-to-person differences, but it's a little bit more complex than that. So you can't just say 0.26 plus 0.32 should add up to what? Oh, it adds up to 0.58, roughly. So all of these measurements, ICC and R squared, are all trying to capture how much variance is explained, but they're combining different pieces, and it can be complicated, and it can be hard to decide which one of these you should report. And the answer is there's not one that you always should report. It depends on the situation. The most important thing to keep yourself from going crazy is to remember you can't really pick wrong. There might be one or two that are better than one or two others, but the most important thing is to pick one and go with it, and make sure you document which one it is you are reporting. If when in doubt, report one or two. I wouldn't report all 4 for each model. But if you knit your R notebook, you have supplemental material that'll include them all for anyone else that's interested. Does that help with R squared and ICC? This is good. R squared and ICC are not going away. They're in every multi-level model, so they're good to address now.
Just sorry, one last question. For the conditional R squared, I guess I don't understand totally how it's different from conditional ICC. Like, what else does it include?
So the conditional R squared should be the adjusted ICC approximately. And I think it has to do with the way the formulas are really written, that why they differ. Because, and I think also one thing is that ICC row R squared, rho squared, still proportion of variance. R squared value is appropriate for mixed models with random slopes. The ICC is really only appropriate if you have 2 levels, and you don't have random slopes. Now this model didn't, but the next model has random slopes in it, right? Oh, and did I have you do ICCs? I didn't have you do ICCs for it because it gets more complex when you add in those random slopes. So I think the 0.43 and the 0.58 are trying to get at the same thing. But remember, how many R squared formulas are there? We could use a different R squared formula. Like I think, let's see if we can do McFadden's or, let's see, what's some of the other ones? Let's see if I can get it to do R squared TJUR, but doesn't like that one. Let's see if it'll do a Cox-Snell. Some of these cannot be applied to every kind of model. There is an R squared and another package. SJ Stack's depreciated. There are a couple more. I'll try to get some more documentation up about all the different ones and why you would go with some of them. It's not a major thing I want us to really like get into, but it is an issue because you're going to need to report R squared because it's a measure of effect size. R squared is more applicable to various models. ICC really is usually only those null models, the truly null models.
Okay, that was helpful. That was really all I needed. Thank you.
Okay, so residual diagnostics we need to do. So I got to get model 5 fit. Where's model 5? There we go. I'm calling it 5. It can be a different number for you. This is my final model in this key. This does not mean this is the only way to get credit here. That's why there's the interpretation and the prompts for you to tell me. So I've got OBS, the effect over time, differing by group and sex, a 3-way interaction. That's what I have in this model. And so the interaction plot, but it's the residual diagnostics that people wanted to look at. So the easiest way to do residual diagnostics for these multi-level models right now, I found some other ones, and this is pretty good. SJ plot is the package name, plot model is the function, but you have to put in type equals diag for diagnostics to get, or else it'll try to plot the actual model or something different, or the coefficients. It's not what you want. Okay, so let's look at the first one. These are nice in this package because it tells you at the top of the plot what you're supposed to be looking for. So this one says the dot should be plotted along that line, that blue line there. So who had questions on this? Is this one of them that we want to talk about? Is this okay? Or is this problematic? Got a couple of thumbs up. Anyone worried about this one? Carly saying maybe. What is it, Carly, that's making you kind of wishy-washy?
I mean, I feel like it's probably good enough. I mean, it looks like slightly, what is it, like sigmoid shaped, I feel like at the ends, but it's probably not
see how
extreme
the
enough.
ends are kind of wonky. They're not straight. Yeah, so this is where students are always like, well, how do I know if it's good enough? And the answer is there's no cutoff. So I like to pair this one with looking at the histogram. So is this perfectly normal? It's not perfectly normal, but you're never going to get perfectly normal, especially with multi-level. But is it normal-ish? If you look at this one, I think most people are a little bit more comfortable making a call on this density histogram-ish plot. It's fairly symmetrical. It's slightly squished. It's definitely unimodal. It's a little bit more peaked, and that peakedness and then the tails kind of being shaped different, that's what this QQ plot's picking up in those ends kind of flaring. So I think together we can make the case that normality's not that far off. It's not perfect, but it's not that far off. Now, the bigger your sample, the more points you have here to stabilize it. So it's okay if a couple are wonky on the ends. If the whole thing is making a curve, or you only have a couple points, so half of them are wonky, that's problematic. But it looks like the minority is really the minority at these ends that are really off track. Okay. So this one is not truly residuals. This one are the BLUPs, the best linear unbiased predictors. So it's looking at the random effects for intercepts, and we had slopes in this one, random intercepts and slopes. That's why we get the 2 panels. But again, we're looking to see the same thing as the other QQ plots. Are the points on the line? This one just gives us confidence intervals because they're a little bit more wiggly. So you kind of squint your eyes and look, or do I have mostly a straight band? What are people's feeling? Okay, terrible, Mike's saying a little bit. Julie's a little bit. Can't see your hand, Megan. Are you a little bit? You good? Yeah. I think this one's fairly good. I think this one's actually maybe even a little better than those other residuals. But it's definitely not totally off track. Now this one, this last one, this one probably creates the most nerves in people for calling this is okay. Who's concerned about this one? Julie, Mike, Chung-Soo, Joey? So what's the first thing that jumps out at your eyes when you look at this plot?
The fact that it's in strips, but you explained yesterday that's from the longitudinal nature of the data.
Because we have clustered data and we have only certain observations and only certain people, that's what causes this stripping effect to happen. The striping is okay. You don't have to worry about it. It looks wonky, but it's not concerning. What we really want to look at is what it says here. We want the amount and distance of points above and below the horizontal line to be about balanced. Now in the middle, we have the most points and we have the most spread. But as we go from left to right or right to left on those ends, are we roughly the same amount above and below the line? It's fairly good. Now it's a little bit wonky, but I think that's more of a fact because we have the stripping due to the multi-level model going on. So even though it looks weird, I think this one is fairly okay. Not perfect, but this is like wild-caught data okay.
So these are just all, again, taking the residuals from the new model and pretty much graphing all the residuals in these different ways.
Mm-hmm.
If you were just to,
yeah, what?
You were just to graph, like if we were just to do a mean line of all the data and graph the residuals, would they look, I mean, does it always kind of, would those just be the same kind of too? Like the residuals?
So, like, that's like the Null model was just, was it 0, 0? Was that, what was, yeah.
Oh yeah, what would that look like?
Here's the Null model. So the Null model is not good because it doesn't have anything in it. Let's compare. Look at the Null model. Can you see these residuals? See how we have more waviness in that line?
Mm-hmm.
This one, it's a little bit more drift, but check out this one. How does that look?
Ooh, not good.
I think this one you're like, whoa, that's not normal. That's almost bimodal or skewed or something. We're not like looking good. And here's these residuals. Now, we still have a little bit of striping, but check out that blue overlaid line. What's the general trend? It's going up. It points out that this model is probably not a great one. This is the Null model. We know it's not great, but it's our starting point. Yeah?
Cool.
And then if I go back to, this is the final model that I chose based on being best at prediction. Now this blue overlaid line, see how it's kind of swinging like a line between power lines? But in general, it's not going up or down. We're not seeing wide fanning out as we go from one side to the other. There's lots of ways it can look funky, but we want to just say overall, is it about balanced above and below? Now on the ends, both ends are kind of going up a little bit, but again, that's an artifact of the stripping versus, and again, I wish that people publish this more so you guys could see more of these to get a better feel. Here you can see that it's not just stripping. There is a clear up, pattern in that blue line. It's not just kind of noisy, it's a pattern. Okay.
Cool.
Any other homework questions while we have it up? Okay. Can you see how everything you learned in 7610 about regression is still here? Just like amplified?
I wish we would have learned it all in R though, or at least me.
Yeah, well, it depends on who you take it from. If you take it from Sarfraz or Tyson, you do.
Oh.
So I think Ryan Knowles is about the only one that's not teaching it in R right now. And he teaches it for the distance cohorts. And he's thinking about swapping. Okay. All right. How are we doing on our break? We got 5 minutes. Okay. Before we go to the break, I want to come to the next homework and look at it with you. Now, this homework 6 is not due till Thursday, but wrap it up, get it in. There's a discussion board to go with it. In fact, let's go to the discussion boards. So I know not everyone's been on them because there's only 11 comments and there's 13 of you and you need an original comment and a reply, but you have time for that. Then the reading you're supposed to be doing right now that's due Thursday is about logistic regression. Now, in logistic regression, there are 2 chapters out of the Hoffman book, which I know you guys don't have. I didn't require it. It is a phenomenal book if you want to reference, especially this is great for non-normal data, categorical, count, or other kinds of outcomes. Phenomenal book for single level regression. I see I got it. I refer to this all the time. This is the one I have. Well, the photocopies I think are from the earlier version of this. I think this is a 2014 version. And I think that it's a 2004. Most of it hasn't changed. He does do all of his software in here are with Stata. So John Hoffman, who wrote this book, he's actually at BYU, the other school down south that we don't speak about. So that might give you an idea if he's at BYU, why there's some of the data sets that are in here, because there's some of the things that he studies down there. There's a lot that are about religion and stuff. Anyway, I just might give you a little background, but really,
What's the
really
name
great.
of that book? What's the name of that book?
I
Okay.
have a link for it in the homework, but John Hoffman, if you want, I can put a link on it. I think on
No, that's totally fine. That's good. Thank you.
$50, I think. It's not bad. I mean, there's lots of great regression books. This is another one of my favorites, but it doesn't have a lot about Andrew Hayes, or this is Darling and Hayes has another one that's really good, but they don't have a lot about logistic regression, multinomial, ordinal, and Poisson and negative binomial, all those other types of regression. This one does a better job at reviewing them. I'm a geek though, I have all of them because I like them. So logistic regression is one of those things you should have covered in your 7610 regressionist class, but it's one that I find is usually not as strong in your repertoire as maybe it needs to be, and it needs to be firm before we do multi-level logistic regression. So these 2 chapters, so chapter 2 is about the idea of generalizing regression, and chapter 3 is on logit and probit regression. I'm not going to cover probit. It's not used as nearly as much in most fields, so just logistic. And then in the encyclopedia, I have 2 chapters in the encyclopedia that go over some examples. And last night, I took the examples in his chapter 3 and wrote them up and put them in the encyclopedia. So as you read this, the chapters, you can follow along in the encyclopedia, and I've done it in R because he's doing it in Stata. And you can also refer for the homework. And then I put up this, I know there's a lot of them. There's like 6 or 7. These are all the StatQuest videos. Most of these are short, 9 minutes, 5 minutes, 11 minutes. But it starts right back. What's the difference between probability and likelihood? What's the difference between odds and log odds? And very simplified to help firm up your foundation, because if that's still wishy-washy, forget doing multi-level logistic regression. And so I would highly suggest watching these. There's also Tyson for his 7610 class has a logistic regression lecture that's recorded. This one's a little bit longer, but it's optional if you feel like you could use a little bit more instruction to get you up to speed on logistic regression. Okay, so I'll show you the homework assignment and then we'll take our break. And then we're going to come back and we're going to look at some of these examples of logistic regression. So this is the new homework assignment. So you have 2, and this is looking really big on my screen. It might not be so big on yours. There are 2 options for homework 7. You pick one. Don't have to do both of these. Just pick whichever one you want. Option A, I just created an assignment, and it is the assignment out of the textbook, Hoffman's textbook on logistic regression. And it just follows exactly what his chapter does, doing logistic regression step by step in R. And it's just like all of ours. Here's the data set, here's the skeleton, and here's the skeleton knitted for directions. The other option, if you don't want to do that, you have this second option to create your own assignment. Now, there's a good chance that when you guys graduate, wherever you go, you're going to be teaching some kind of introductory stats classes, as if you're going to be a faculty or an instructor if you're going to stay in academia. So you can practice, another option, creating an assignment, and it can be on any of these: logistic, or Poisson, negative binomial, ordinal, multinomial, any of those methods. We haven't done the reading on them, but if you want to work on that, you can. And get a data set, make your own key and your own skeleton and knit them. And so you'll turn in your data set along with the R markdown file for the key and the skeleton, and then the knitted PDF for the key and the skeleton. So it's just another option if you want to take it. Okay, so we need at least 5 minutes off. I'm going to pause it unless anyone has any questions before we break. Okay, then push pause. We'll see you back here in 5 minutes. Recording. All right, so we're back from break. Yay, we actually got an on-time break today, finally. And we have, what, 38 minutes, so just over a half hour to cover some logistic regression examples. So I am unaware right now of your history and expertise in logistic regression. Anyone consider themselves pretty expert, could do it in your sleep? Not surprised. Anyone feel like, yeah, I've used it a little bit, I can read about it and kind of get the gist of it? Anyone there? Yeah. Anyone like, holy heck, we learned this? Yeah? It's okay. You don't have to raise your hand. You do it in your mind. It's okay. We're going to start a little bit slow. We don't have a ton of time, but those StatQuest videos really help. I watched them and I was like, oh, even after all these years and decades, I was like, that's really good. That makes sense. Oh, he does some visual thing with the going from the logits, from the probability scale to the logit scale. I'm like, oh, that's so much clearer. So even if you think you're expert level, it's worth your time. Okay, so this is in the encyclopedia. Now, when we've gone to the encyclopedia before, we've gone to volume 5 on multi-level modeling, right? And we did volume 0 on installing all our software. Today, I'm going to go into volume 4 on single level regression. Now, this is not clickable. If I try to click on this thing here, nothing happens. So I have to come up to volume links and then hit this colored strip. And I got to figure out how to make it better. This website's written in R, very, very basic. So this will get you to volume 4, and it's titled multiple linear regression. It should be single level regression or just regression analysis. So it starts out with correlation, simple linear regression, multiple linear regression. I have a little playground thing, some interactions. But what we want are these later chapters: logistic regression and extensions, and then count outcome regressions. So these first two, the bronchitis and the maternal, can I stretch this? No. These are 2 of my examples from other books. 10 and 11, the numbers might change, are on depression and volunteering, religious volunteering. These 2 are out of the Hoffman book. And then extensions are my own examples. And then I'll be adding the other examples in, because our next reading set starting on Thursday will be on multinomial and ordinal logistic regression, Poisson and negative binomial count regression. I think all of these you don't need to be an expert in. I think logistic you have to be somewhat secure in because it's so common. The other types of regression you can kind of just have more of a passing understanding of. So that's why I'm focusing today on logistic. And if you can get logistic regression, the other ones aren't so much of a stretch. Logistic is a big leap. So I'll be adding chapters in here. So again, these chapters 10 and 11 on the depression and volunteering, those are the ones in your chapter 3 Huffman reading. So again, pull it up and, you know, like side by side while you're reading if you want.
How do you change volumes again
Volumes,
in the encyclopedia?
I'm still in 4.
I'm in 5.
Yeah, so if you're in 5, let's see, let me go to 5 and I'll show you how to get
I
there.
can't see how to switch.
I'll show you how to switch. It's kind of convoluted. I need to come up with a better way. So if you're in 5, because that's what our Canvas homepage takes you to. So in Canvas, if you click on the encyclopedia button right here, it takes you to volume 5. If you're on the welcome screen of volume 5, it says right under welcome, it says background and links to other volumes can be found at, and then it says the encyclopedia's home website. Click on that encyclopedia's home website. That takes you to the landing page. Then you have to go into the upper right-hand corner. This is the part I've got to fix to get the volume links. And then you can click into volume 4. So Jill, that was a really great question because I can see where that would be confusing. Did you get there?
Yes, thank you.
Awesome. Okay, so I'm going to this bronchiopulmonary dysplasia in premature infants. You can tell that this was not a social science example, but still it's pretty concrete. So that's why we're going to go with it. Some of the social science examples are harder to use for introductory because they rely on having a functioning content knowledge. This one, hopefully we can understand without having any of the theoretical content specifics going on. So we're going to use a lot of the same packages before. We're going to use tidyverse, TechReg. Now, when we go to Generalized, TechReg, remember, makes those tables, but the parameter estimates for generalized regressions are usually on the link function. And so we want to unlink them to get back to the response scale. So I cannot find a package that did that for multi-level modeling. There are some out there, like there's the this SJ plot ab model can do it, but only in HTML, so not in text and not in LaTeX. And so I made up my own little package. So proud, my first package with Tyson's help, and I called it TechReg Help R. But it's not on CRAN. So the first time you use it, you need to take this line of code here to download my little baby package from GitHub. So if you just highlight this command, remotes, install GitHub, Sarah Boyer Schwartz is my social media handle, and TechReg Helper. If you just copy that and then go into R in your console, the console is the one over here that says console at the tab. It could be at a different location, but if you just paste that line in there and hit enter, it will go get your package. Now, mine gave me this message because I already have it. And it says, it doesn't have anything new. You don't need to do it again. Okay. But you'll need that little package because it helps you exponentiate your betas so that you can interpret them. I couldn't find anything that did it better. So, and then there's just some, here's our interactions package, our SJ plot, and that performance package. So we're using a lot of the bits and pieces that we use for multi-level and single level. They all play together. So this study, like we said, is bronchiopulmonary dysplasia, or it abbreviates it BPD. And this is a study on low birth weight infants in a neonatal intensive care. So brand new babies, a lot of them premature, have problems breathing, a lung disorder, chronic lung disease, and it's called bronchiopulmonary dysplasia. And it's especially a problem for premature and very small babies, and they struggle to live. So this study is 223 of these infants, and all of them in the study had to be less than 1750 grams. These are little tiny babies. And so our response variable is binary. It has 2 levels, either yes, they got this thing, or no, they didn't by 28 days of life. So we're defining this disease or this issue when they need both oxygen and they're taking a chest x-ray. So those are the two things that qualify as having this disorder. So it's either yes, they have it, or no, they don't. Why is this a problem? Why can't we do regular regression with this dependent variable?
It's not continuous.
It's definitely not continuous. There's only two possible values, yes or no. They have it or they don't. Now, if they're developing it, they're still in the no until they meet the criteria to become a yes. So that's our main variable, BPD. That's our dependent outcome Y variable. And we have these three main predictors: the birth weight, which is how many grams the baby weighed when it was born; gestational age. Does anyone know off the top of their head what's full term for a baby?
40 weeks.
40 weeks is full term. My first baby was 36 weeks and 2 days, and that's the day before the cutoff. Premature is anything that's more than 4 weeks or more early. But so a baby born at 30 weeks is premature. At 27 is quite premature. 39 to 41 is totally normal, give or take a couple weeks. And then toxemia. Anyone know what toxemia is? No? Toxemia is a condition in the mother that often happens in, especially later in pregnancy, that can lead to strokes in the mother. And it's picked up by having high blood pressure. So it's a problem in a pregnant mother that gets really high blood pressure and has a risk of throwing a clot for a stroke or a clot going to the lung. So it's kind of dangerous. So usually when the mom has toxemia, the treatment is to deliver the baby. So a lot of times if you get toxemia, you have a C-section immediately. So some of our predictors are continuous: birth weight in grams, gestational age in weeks. Those are continuous variables. But our other predictor variable, our independent variable, toxemia, is also a yes or a no variable. So logistic regression is like regular regression. Your predictors, your independent variables, can be continuous or categorical, or you can have some of each. It doesn't matter. Okay, so here's our data set. This is the raw data set. So this first baby, yes, had this BPD. They were born weighing 850 grams at gestational age 27 weeks, and the mom did not have toxemia. Compared to like down here, this fourth line, this fourth observation, the baby did not have BPD. They were born at weighing 960 grams at 35 weeks gestation, and mom did have toxemia. So for logistic regression, you need to leave the outcome dependent variable coded as zeros and ones. You do not want it to be a factor. You do not want it to be labeled. You want it to be a DBL, that's what it says right here, or an integer. So we see just zeros and ones. You don't want to have letters or words in your outcome variable, or else it won't fit. It'll throw a warning. But your predictor variables can be. So I've taken my raw data set and I've cleaned it up by taking the toxemia variable and making it a factor where I give it levels. That makes it easier to look at the outcome or the models. So when we fit a linear regression model, we use the command LM, linear model. Linear regression is LM. To go to logistic, we have to do GLM. Coding, not so bad so far, right?
Except it sounds like generalized linear model.
Generalized. Now,
that's what that is?
Yeah, so there is a little, abbreviations are tough. So there's general linear model and then generalized linear model. So general linear model, GLM, usually just means multiple linear regression, simple linear regression, ANOVA, and t-test. The generalized with the Z on it means that it can be logistic, Poisson, negative binomial, all these different flavors or distributions with link functions. But sometimes we use GLM to mean general, and sometimes for generalized. I'm sorry, was not my choice. I would put the Z on there. And sometimes you'll see it GZLM to make sure that you know that it's generalized with some other distribution and link function. So, which brings us to, you need a distribution and a link function to generalize it. Logistic regression uses the binomial distribution, that's the yes or no part, and to make it work, we use what's called the logit link. Logit or logit, I was taught to say it logit, is the log odds ratio. So it's log odds, shortened to be logit. I didn't make that choice either. So to fit the null model, instead of saying LM, we're going to say GLM. Null model would have no predictors, so it's the outcome variable that's zeros and ones, tilde wave, and just the number 1 for no predictors. And then just like before, we have what the data set is that we're using, and then this is the new part, family equals binomial, and then in parentheses, link equals logit. Okay. Now, how is that different than the second model down here? How would you describe the second model that I'm calling model 1 in comparison to the null model 0?
It has predictors.
Has predictors. Now, what have I done with weight? The birth weight. Can you see that? What did I do?
Did you convert the, I don't know, from grams to milligrams or something?
Yeah, I did a conversion. I took the grams and I'm dividing it by 100, because if I leave grams are tiny. And if I leave it in grams, then my beta will tell me how the increased probability in having this disorder for every 1 gram heavier a baby is. And 1 gram is a tiny amount. So I'm taking their weight in grams and dividing it by 100. And it's going to be, what is that? Would that be what is the multiple of 10? It's not getting smaller to be bigger. So it's like, what's the metric system? There's deca going bigger.
You think kilograms 1,000?
Kilograms 1,000. So what's 100?
I don't know.
Deca 10, whatever it is, it's a multiple of 100 grams. So a baby, instead of being 900 grams, would be 0.9 decagrams or whatever these are. 100 gram increments.
Probably like centigram.
Cent is when you divide by 100. What is it when you times by 100? I'm gonna have to look up my metric system conversion. Okay, and then gestational age and toxemia. So this is the main effects models. No interactions in sight yet, but I did re-weight or rescale the weight so it wasn't in such small increments.
You can,
Yeah.
in that main effects model, you can have continuous or factors or both as predictors.
Yes. All regression-based models could have continuous predictors, factor categorical predictors, or both as main effects or interactions.
So it's only the DV that has to be coded in that specific way. Okay.
Yes. Thus far, everything we've done, everything had to have a continuous DV, dependent variable Y. Today, we want that dependent variable to be zeros and ones. But the predictors can still be anything, any format.
And what's the I in front of the birth weight divided by 100?
The I with the parentheses says, in this model, internally take the birth weight and divide it by 100. Yeah, that's good to know because it's specific to R. That's how you do it in R, is to internally inside this model, take birth weight and divide it by 100. So the units are changed. So it's per 100 grams instead of per 1 gram. So you can ask for the log likelihood of the models. You can ask for the AIC, BIC, all of those things still exist for generalized models. And the deviance is just negative, it should be -2 times the log likelihood. I don't know what's going on there. And so we can ask for AIC of a model, BIC of a model, but there's a little hiccup when it comes to R squared. Remember, R² doesn't work the same way for multi-level models. It also does not work the same way for generalized models. And there's a really good StatQuest video to break that down visually for why. One of the most common types of R² formulas for logistic regression is McFadden's. It is starting to fall out of favor, but in the past, social sciences especially have used McFadden's pseudo R². And you do a fraction with the likelihoods of the model you're using to the null model and subtract it from 1. And there's also Cox and Snell and this other guy. And this one is the one that's now becoming more in fashion. Or you can use this package and it will spit pretty much all of them out. So this is Pscl, is the package name, PR² for pseudo. Pseudo starts with the P. R², and you give it the model name. So it gives you the likelihood for this model and for the null model, G², but here's our McFadden's R² and some other R²s, or you can ask for them separately. If you are submitting a manuscript for publication, how do you choose which R² you should use? Let's look. McFadden's is 0.29. This one's 0.31. This one's 0.43. Which one should I report? Don't choose the biggest one. I would look in the journal that you're targeting to see what other people have used. And you can do a quick Google search, or you could talk to me. Sometimes the preferred R² is the one that other people are using to facilitate meta-analysis, not just because it's the best one, but it's going to match what other people are using so that we have consistency in a field. So sometimes we'll go with an effect size measure to be consistent rather than because it's the best. We use Cohen's d, even though we should probably use omega². But Cohen's d is what SPSS spit out for years and years and years and years. So that's what everyone has used. So we keep using it to be consistent. Not a good reason, but there it is. Okay. Coefficients. So the coefficients are the betas. Now in this model, we have an intercept. We have the birth weight divided by 100, gestational age, and whether or not the mom has toxemia. We have 3 predictors. I can say for this model, give me the coefficients, and we get all these beta coefficients. But these are on the Logit scale, which is log odds, which makes no sense to anyone. So what we need to do is to go from the Logit scale to the odds ratio scale. And the way we do that is by raising everything to the power of e to the power of that number. The way you raise the things so that they're a power on e, it's a little curly e in math, that natural logarithm based number, is to exp. So we exponentiate it is how we say it. So we're going to take this model and we're going to get its coefficients, and then we are going to exponentiate them. This turns us from having the Logit scale to having the odds ratio scale. So now we've got this other set of numbers. Let's look at interpretation. Now, this number has an e to the -1. That means times 10 to the -1. It's shortcut for scientific notation. Why they used e again, I don't know. It's craziness. But what is this number if we don't use that scientific notation? It's
0.767.
0.767. So it's about 3/4. 0.75-ish is 3/4. So this tells us for every 100 grams heavier a baby is, the odds ratio is 3/4 what it was before. So if a baby can stay in and gain 100 grams, their risk goes down by 25%. Not their risk, their odds go down by 20%, 5%. We have to be very careful with the languaging here. It's very easy to get lazy with the languaging. This is how the odds change. So for odds ratio, you always compare it to 1. If an odds ratio is 1, it means stays the same. If an odds ratio is smaller than 1, then our odds are going down. Here the number is 0.7, let's just call it 0.75 to make it easier. That's lower than 1. We have to compare it to 1 and say how much lower than 1. It's 0.25, 0.24 lower. So that tells us 100 grams heavier baby has 24% lower odds of having that pulmonary disease disorder thing going on in it. Now, what about gestation? It's got that E-1 thing in it too. So what's this number if we make it a decimal, pure decimal? It'll be 0.68. So you compare that to 1, it's less than 1. So subtract 1 and 0.68 and you get 0.32. So that means if the gestational age is 1 week older, the odds go down 32%. And this last one, what's this decimal? 0.26. That's a lot smaller than 1. It's almost 75% smaller than 1. So if the mom has toxemia, the baby's actually 75% less likely to have odds of having this disease. And it seems weird, but the reason being, if mom has toxemia, that's a problem with mom, and the baby's being born early because mom's having an issue, baby's fine. They just are born small just because mom had to get them out, not that they themselves were sick. Versus if you have a small baby in general, it usually means the baby's sick or the baby's not growing well. Remember, all of the babies in the study are small or early. So if mom has toxemia, the baby's being born early through no fault of their own lungs. Whereas if mom doesn't have toxemia, they're more likely to be born because of restricted growth, or the baby showing some stress or has some birth defect or some other reason for early delivery that's counter to toxemia. Okay, so we can use our ANOVA command to run a likelihood ratio test for logistic regressions just the same way, but it doesn't happen by default. If you say ANOVA and give it 2 logistic regression models, it won't automatically do the likelihood ratio test. It gives you this nice little table of deviances and residuals, but it doesn't actually do a test. When you're doing likelihood ratio, you have to tell it that you want to test. If you have 1 model, you can say test chi-squared, and it will do this thing. But if we have 2 models, we want to say test equals, in quotes, LRT. And I'll show you one of those in a second. Okay, so to get the output, the raw output on the logit scale, we can summarize the model. But again, this looks like regular regression output, but the coefficient estimates are not on probability scale, they're not on odds scale, they're not even odds ratio. When you just say summary of the model, these are on the logit scale, so don't look at them necessarily. You need to make a table. Now, this model tab makes a glorious table that gives you already the odds ratio, but this doesn't work with a PDF. So this is where I'm going to switch over and do TechReg. So here's our nitreg. I just updated this last night. So we're going to use TechReg nitreg, our model, like usual. If you do that, just usual, the default is to give you the parameters, those betas in the logit scale. Really hard to even look at. I mean, we can look at our wall tests to know if they're significant, but interpretation, they're really junky. I'll say it. So what we can do is exponentiate the betas to get something we can interpret. And this is where my child package comes in, the TechReg helper. So inside of the knitter, TechReg nitreg, we're going to use the TechReg helper package. And this is my baby function, extract from a GLM by exponentiating, and give it the name of the model. This will then give you the odds ratio. And almost always, this is what we publish for logistic regression, is not the betas in their logit scale, but we exponentiate them to get them onto the odds ratio scale. So here we can see for birth weight, what's the exponentiated beta? 0.77. So every 100 grams heavier a baby is, the odds of that outcome goes down 23%. Where did I get 23? This is lower than 1. How much lower? You subtract 0.23 to get to the 0.77. For gestational age, for 1 week older a baby, the odds go down 32%. If mom has toxemia, yes, the odds go down 74% versus if she did not have toxemia. So this TechReg helper function is really nice for exponentiating the betas so we can interpret them for logistic regression. Now, here's a table that has the betas in their logit scale, and here's a table that has them exponentiated in the odds ratio scale. Sometimes it's really helpful to have both. And so you can put them together. So notice I'm doing a knitter reg, and I'm listing the same model twice. Here I've listed the name of the model by itself, and here I put it in the extract function. I've also turned off all these AIC, BIC, log likelihood, deviance, and number of observations. Because if you don't, it repeats them over here. So this table has both the betas and the standard errors in their logit scale, as well as the betas exponentiated to create odds ratios. And we've got odds, with the odds ratio, we have the confidence intervals instead of a p-value or a standard error because it's not symmetric. So plotting the model, let's see. The best way to plot these models is with our friend SJ Plot. Yeah, question?
Yeah, can I ask a question again about the interpreting of the odds ratios?
Mm-hmm.
So with the continuous one, I guess the toxemia, yes or no, that makes sense.
Mm-hmm.
With the birth weight, this 77%, or down 23%.
Down 23%.
Every of the previous every 100 grams then?
Mm-hmm. Now, this is where logistic regression is different than linear regression, regular linear regression. In linear regular regression, for every X unit you go over, the beta is how much you add going up. It's additive. In logistic regression, the additive is only in the logits, and it turns into multiplicative in the odds ratio. So that's why we don't say the odds go up 0.2. We say they go down or up some percentage. So if a baby is 100 pounds, so here's a baby's risk. What if we can keep it in long enough that it can gain 100 more grams? It goes down 23% of what would have been before. If we go up another 100 grams, it goes down another 23%. And you have to think multiplicative. Has anyone ever been to a store that's had a sale like 20% off? What do you get at the register if I have a 20% off coupon and a 50% off coupon? Is it 70% off?
No.
Why? Don't
because
you?
I was just gonna say the new percentage you take off is off a different whole, like the whole amount is a different one. So
they're not subtracting like $50. If I had a $5 off and a $10 off, that would add to $15 off. But when we have the percentages, it's multiplicative. We take our total and we multiply 0.20 times that comes off. And then what's left, we take 0.50% off. So we are multiplying. And that's the same way odds ratios work in logistic regression. So even though for each 100 grams a baby's weight goes up, the odds go down 23%, is it ever going to get to zero? If here's the chance, go down 23%, go down 23%, go down. Every time we go down 23%, are we ever going to get to 0?
No.
It's like, it's a logarithmic scale. If I used to do this with my high school math class. I would stand in the room and I'd point to the wall and say, okay, I'm going to cut the distance in half. How many times is it going to take for me to get to the wall? How many steps? My first step, I cut the distance in half and get closer to the wall. Then I take another step and cut the distance in half. You ever seen a football game where someone they're in the red zone and they get a penalty and they get half the distance to the goal? And then they get another penalty that's another half the distance to the goal. Are they ever going to reach the goal that way? I mean, at some points we're going to reach the tolerance and we're going to call it close enough, but we never actually get to 0. It's the same thing with logit. We're multiplying by a fraction that makes it smaller and smaller, but never gets quite to 0. Okay. This is a much different way of thinking. And again, the reason that I'm pounding this is because you got to understand it in single level to be able to think about it in 2 or 3 levels. And I just don't think you guys get enough training in it or use. Okay, so we've seen SJ plot model type equals pred before, right? You're doing it on homework 6 for the longitudinal model. We can still use it and we get, so here's birth weight. It's flat. Wait, I thought we just said it went down. Well, it is kind of going down, is it? It's going slightly down. Because look at the scale, 100%, and this is basically tiny percent. Okay, here's gestational age. So down here, look, it makes the scale really nice. The baby goes 25 weeks old to 37 weeks old. What happens to the probability of having that disorder? As the baby gets older, the chance of having that goes down. So if you're pregnant, what do you want to do? Keep that baby in. Okay. And then for toxemia, because it's a categorical 2-level predictor, we have a different kind of plot because toxemia can only be yes or no. Which option has a higher chance of having the baby have the pulmonary disorder? Worse outcomes if the mom
Has toxemia.
does not
Does not have toxemia.
have toxemia. If mom does have toxemia, it's smaller. Now I want to point out, look at those confidence bands. What do you notice about the whiskers on either side, up and down? Are they the same length? No, because there is a cap at 100%. Can you have more than 100% chance? No, and logistic regression adjusts, so that's why those whiskers are like shorter on one side and longer on the other. They're called profile confidence intervals, not walled confidence intervals. A walled test, we take the beta and divide by the standard error to get a t-value and a p-value. A walled confidence interval, we take the estimate and we add or subtract 2 standard errors. These are profile likelihood confidence intervals that are asymmetric to more accurately reflect the reality that the chance has to be between 0 and 100%. It can't go beyond that. Okay, you can use the interactions interact plot to do multiple variables. So all of the same tools we've learned in R still apply. Now, when you do an interacts plot, by default, it will do the logit scale. Notice it, our scale here's 0, but here's -2.5. That doesn't make any sense. That's the logit scale. And it's because I put in outcome scale equals link, the logit scale. To get it back on the probability scale, you have to say outcome equals response. Now, what's the response? What's our dependent variable again?
BPD status.
The disease status is either yes or no. So the original response is going to go from 0 for a no to 1 for a yes. That's the probability scale. So notice when I put in my interactions plot, interact plot command, I add the option outcome dot scale equals response, we go back 0 being no, 1 being yes. What do you notice about all those curves? They're all starting at a high chance and then going down to a small chance. And these are probability. And this one's on weight. And here we have 2 panels by toxemia, because those are the 2 variables I told it to do. Oh, and what about gestational age? So it's doing, the pred is the main x-axis, mod x is the different lines, and then if you add a mod 2, it does panels by it. So you can get a picture that includes 3 variables at once. So if you don't say otherwise, it will use, for a continuous variable, how does it make different lines by continuous variables? By default, it will choose the mean plus or minus 1 standard error. But if you're interested, you can tell it which values to plot for. Like, I know most of the babies are born in the late 20s or the early 30 weeks. So I want to choose those specifically to display. So I went from basically letting it do a lot of default behavior to specifying a lot of things so that it's more of a publication quality plot. Now, I'm not going to spend a lot of time going on all those things, but I just want to point out that there is code on the encyclopedia if you ever want to tidy up your plots to make them more publication worthy. So, logistic regression in a nutshell, 1 example down. You're not an expert, but you have some reading, you have some YouTube videos, and you have a homework assignment to play around with. So the reading has a discussion board. Homework 6 discussion board and assignment are due on Thursday. You have a week from Thursday to get this assignment 7 done in. So you have a little while. Don't put it off, but you have some time to work it into your schedule, and I'll make a discussion board for it as well as the other readings. So you've got a couple things due this Thursday, and you'll have a couple things doing the following Thursday. And then this Thursday, we'll go over more kinds of generalized regression, like the Poisson negative binomial and ordinal and multinomial logistic. Okay, I'll hang around if anyone has any questions you want to ask.
Thank you.
Time's up.
Thank you.
Thank you.
I had a question, Sarah, because I'm wondering if it makes sense to try using a logistic regression for one part of my own data.
Mm-hmm.
And I'm curious what you think, but that might not be relevant to other people.
Alex, do you have any other questions?
Yeah, I had a question, but I can wait until Carter's done if he wants to go.
Well, it sounds like Carter wants a brainstorm session, so maybe we should ask your question first.
Can you go back up to the table?
Yep.
So and so how in that do we know that it's going down and not going up? Because like 0.77 doesn't have a negative. So is it based on the...
Okay, so if the beta is negative in the logit scale, the odds ratio will be less than 1. So we're used to seeing if things are positive or negative on either side of 0. But when we're talking about odds ratios are a fraction. And if they're the same on top, if we have 50-50 odds, the top and bottom are equal, 50-50, and it divides to equal 1. So you have to train your brain on the odds ratio, these exponentiated betas, to say, are they above or below 1, instead of saying, are they above or below 0? So I know that they're going down because these are all point something. They're 0.77, 0.68, 0.26. If it was going up, it would be like 1.27 or 3.7.
Okay, that makes sense. So then for interpreting those, we would say like for like a 1 unit increase in the gestational period, whatever that would be.
It's a week, yeah.
This week, then there's associated, what is it, 0.20?
32% reduction.
32%
odds.
decrease in the odds of the outcome.
Yes. And it's tricky. It's very tricky because we're so used to saying positive or negative on either side of 0, and that's how much it adds or subtracts. And now we're comparing it to 1 and saying that's how much we multiply the odds. It's very different thinking than we're used to. And that's why I think we need more training to get used to thinking that way.
And Sarah, if you hadn't transformed the birth weight by dividing it by 100, I was just trying to think like, would it?
I can show you what it's like if I don't. It just makes it so that there's the beta is teensy tiny.
Because it's based on the 1 gram.
Because it's a 1 gram. So if, let's see. So here's the model. Here, I will take it. I'm going to copy it here, and I'm going to get rid of the stuff around birth weight. So it's just birth weight in grams.
Yeah.
Oh, I got to run the stuff above it. Helps to have the data set ready. Okay. So now, or I'll come down here to the table and run the table. Where's the table? Here's that, no, here's the combined table. Oh, but it's not gonna have, I didn't run both of them yet. Okay, okay, so notice the beta, and here's exponentiated. It's 0.00, like we're gonna have to add a lot of digits. It's 0.0026.
Yeah.
It's so tiny, it's hard to talk about. And really, how much difference is 1 gram in a baby?
Right. Right.
1
So
gram.
that's solely just based on your measurement units and for the sake of interpretation. Okay.
It's for the sake of interpretation. The R squared, the AIC, the BIC, the log likelihood, all of the fit statistics and the other things will all be identical. I just took birth weight and divided it by 100 so that this beta and the odds ratio weren't so tiny, especially because 1 gram is a minuscule amount to talk about. It's non-trivial, and knowing whether you should or what happened is I did it without doing that, and I'm like, oh my gosh, this is so tiny, I can't even talk about it.
Well, thank you.
Alejandro, or do you have questions, or you just forgot to turn it off? Probably. Okay, Carter, shoot on your. Should I pause the recording?
Very, very quick. I was just curious if you thought that